Okay, so in this video, we are looking at matching the specification points for the reactions of benzene, which include its combustion, its reaction with bromine, with concentrated nitrogen sulfuric acids, with fuming sulfuric acids, with halogenoalkanes and in the Friedel-Crafts reaction, and additional reactions with hydrogen, what the mechanism actually looks like, what's going to happen when we've got methoxybenzene or methylbenzene, we'll look at that in a separate video, and reactions of phenol with bromine water. Okay, so in our benzene ring, we have a structure with 6 p orbitals around the carbon atoms, which gives a delocalized structure, which we can see here. And with that, we get an electron density around the center of the ring. So we get 6 delocalized electrons. So what you can see in that D diagram is electron density being focused in the center. So that's why that patch is red. So that electron density is focused. So you can see there's an even spread of the electron density around the ring. So there's no one point that is more electron dense than the other. So what impact does this actually have on the molecule? Well, if we look at particular reactions, and we look at these benzene reactions, we can see we have a donut orbital overlap of p orbitals above and below the ring, which is delocalized. So that's going to mean that there, as I've said before, there's no source of electron density greater than anywhere else. So these are still going to undergo electrophilic reactions because there's no place where there's a delta positive on the molecule. But they're not going to undergo electrophilic addition reactions, they're going to undergo electrophilic substitution reactions. So what do these reactions actually look like? So we can look at particular examples. For example, if we look at the combustion of our benzene, in this reaction we're getting different benzene molecules and they are having to react with a huge excess of oxygen molecules. So in theory we should end up with carbon dioxide and water. However, in practice, because we need a huge excess of oxygen, all the oxygen is the majority of the oxygen is used up by the hydrogens in the hydrocarbon, meaning that we actually produce quite a lot of carbon and carbon monoxide, and we get quite a lot of incomplete combustion, which is why we end up with a smoky flame. If we can go on to look at reactions where we've got a bromination, so in this case, because there is a delocalized ring of electrons around my benzene ring, there's no point of electron density, which means that actually I need to have a bromocation, which is formed from FeBr3 or AlBr3, to form a bromocation before my bromination can actually take place. So we can look at what the actual mechanism for this is. So this is when we've got alkylation, but the same principle is going to apply for bromination as well. So we've got an AlCl3, which is a Lewis acid, so it's acting to accept the lone pair from the chlorine. And then we end up with this intermediate, which means we form AlCl4 and our R plus electrophile. And then our R plus electrophile reacts with the benzene ring to form a carbocation intermediate. And then the Cl minus, or AlCl4 minus, really comes along to deprotonate that hydrogen. So I form HCl and AlCl3. So my AlCl3 is acting acting as a catalyst. Okay, if we look at the specific reaction for nitration, okay, in the nitration we're starting off with sulfuric acid and nitric acid to make my NO2 electrophile, okay, and we also have HSO4 as a byproduct, okay, alright, and then in that actual reaction, our mechanism looks at first step how we actually make the nitronium ion. So we're starting off to make an nitronium ion, and then that nitronium ion reacts with the benzene ring because we've got electron density, so we have a curly arrow going from my benzene ring to my nitronium, okay, and then I have HSO4 minus. Okay, so that then takes that hydrogen, so I reform H2SO4, which is my H plus there, so the H2SO4 is acting as a catalyst, okay? And then we can also look at reactions with fuming sulfuric acid. Okay, so in my fuming sulfuric acid, I form an electrophile of SO3H plus. Okay, and that's formed by the lone pair deprotonating one of the OH molecules and then forming OH2. And the OH2 acts as a leaving group to form my SO3H plus electrophile. Okay, and then this SO2 H electrophile reacts with the benzene to form the benzene sulfonic acids. Okay, so in this video we've gone through a whistle-stop tour looking at the treatment of benzene with sulfuric acids, the treatment of benzene with bromine, the reaction to form a smoky flame, the treatment with nitric acids and sulfuric acids, treatment with fuming sulfuric acids, with halogenoalkanes to form acyl chlorides and acyl chlorides, okay, and the addition reactions with hydrogen. We've looked at the mechanism for the electrophilic substitution, okay, and in the subsequent video we'll look at reactions of methylbenzene and phenol, but you don't need to look at that for your lesson tomorrow.